All I know is that in the last class, when I was looking at my monitor, it was jet black on mine, but your guys was white. And I know that on mine now it's white, and you're getting black. So apparently there must be something there. I'll have to see if I can figure out what the.
We can't.
Yeah, you can't read the yeah. Yeah. Oh, that's even worse. Oh, okay. Because.
And save it as a JPEG on some other color trend.
Well, it was actually just the.
Alpha channel. Yeah.
Sorry?
Basically, it's because you're some sort of PNG to JPEG conversion turned every transparent part black.
Oh, but there's even more than that wrong, because apparently looking at the one here, you can't even see the letters.
JPEG compression.
So. Okay, so I'll have to. Well, you can't clearly do the quiz, or can't practice that one. So we'll make another stab at it on Friday and see what happens. So, okay, so for today then, did I just start the wrong quiz? Or sorry, the wrong lecture? Yes, I did. Okay, so that won't be very good. That's just. Okay, we'll start the right lecture. Okay. So we're switching topics a little bit. We're going to actually start looking at some things called isolation, and that's how we keep things separate on the internet. And we're still looking at location, and of course one of the big sub-themes from all of this is layering and abstractions. Okay, I've actually posted the new sets of readings for this section of the course, so there's actually stuff in there for ARP. We're going to be talking about multiplexing, so that's something you can read up on. And then if you want to read a little bit in advance, we're going to start talking about DNS, domain naming system, and so that's sort of the next topic. So if you wanted to read ahead, that would be what you should be looking at. Okay, so before I go on, though, are there any questions from last class? Okay, so our big themes today are going to be multiplexing and natting. And it turns out that before you can sort of do natting, you have to understand multiplexing. So we're going to define what multiplexing is. And here's some of the things you should be able to do. These are just taken from the learning goals. But basically, you should be able to figure out how natting works and how that sort of stuff goes ahead. But before we go on with that, I want to take a little bit of a sidetrack. So someone asked a question about something about IP addresses or something like that, how many there were or something. So there's this great little video from Bob Kahn. If I get my mouse over there. If I find my mouse, first of all. Okay.
It's on the screen.
Oh, there it is. Okay. Okay. So this was done by on PBS, of all places. And this is a 1-hour interview with this guy, Bob Kahn, but I'm not going to show you the whole hour. So just a few minutes of this interview. And he's going to talk about when they were, so he's one of the guys who was involved in, as much as anyone was involved in the design of the original internet, which was not by whatever the Al Gore or whoever it was claimed he invented the internet. So he was involved in some of the original designs. Okay? Yeah. And so he's going to talk. He's interviewed. So let him just talk a little bit about how they came up with 32 bits. Okay, so I'm going to shut the lights down. Okay, and oh. And of course, whenever I shut the lights, change the lights, the microphone changes. Okay, and so let's see the audio. Let's roll.
And I think we did a reasonably good job. Could have been better in some ways. Yeah, probably. I mean, I can give you some examples of things that we chose to do back then that in retrospect look pretty silly. You know, we knew that we needed more address space. The ARPANET had 16-bit addresses. The way you address something was you spelled out in the 16 bits, you know, which machine you wanted to go to. Well, guess what? They're all on one net, right? So you need to say what net, but you had to say what node of the net to go to, and then you had to say which wire out of the net. There were 4 wires, so you could connect 4 machines, basically. And so that's what it was. It was sort of like 2 bits to say which of the 4 wires, and then another, I guess, 6 bits to say which of the 64 nodes that you could handle, and so those were using 8 of the 16 bits.
Yeah.
And maybe there were a few more used for other minor purposes, but to first order, that's what happened in the ARPANET. We said, well, if we're going to go to a larger set of networks, we need more bits, so we went to 32 bits. And our thought was,
That's enough.
this is going to be good for the indefinite future. I mean, what we did was we took the 32 bits and said, we'll take the first 8 and use that to designate which net. Well, if you figure out how many combinations of 8 bits you can have, there are 256 combinations. And we figured, well, AT&T would probably have a net of their own, and maybe the Defense Department, that was 2. Maybe there'd be one in Europe, that's 3. We figured, you know, maybe there'd be one in Japan or Asia Pacific or something, that'd be 4. We double it, that's 8. Let's double it again, that's 16. Double it again, that's 32. And no matter how we could calculate it, 256 seemed to be more than we'd ever need. But what did we not think about? Well, we hadn't contemplated the personal computer being generated. We hadn't been thinking about local area nets to connect lots of computers in one building, for example. But within a very short time after that, all of that hit us.
Yeah.
You know, because Xerox PARC came out with their Altos, and the Ethernet came right on the heels of it. So very quickly we realized that 8 bits wasn't going to do it. And so we had to kind of rethink how we were going to deal with that. We still kept the 32 bits. In fact, there's still 32 bits today. It's what's called version 4 of the IP protocol, IPv4. But people are now trying to move toward a 128-bit version, which is called IPv6. And it's hard to make those transitions. Anytime you move from one regime in which all the pieces sort of work together and you try to change some pieces, then you always got the issues of backward compatibility and how do you make the transition happen in a smooth fashion. So that was one of the things that I think we didn't get quite right initially, but we had enough flexibility in the system to cope with it.
Oh yeah, the fact that we're still
using it,
functioning with
Right.
32-bit addressing.
But we knew within 6 months to a year after that 8 bits wasn't going to hack it.
This program was made possible by a grant from the Corporation for Public Broadcasting.
Got to say that part,
This
right?
is Genius.
Okay, so that was Bob Kahn. And if you go and look for Nerd TV, you'll find that. There are like 16 episodes of this and stuff like that. Not all of them are on networking. There's some on computer graphics, some on the creation of the Macintosh computer and stuff like that. What's kind of interesting about it is I think he's the only guy that's wearing a white shirt and tie in all of the interviews that are there, so that's kind of interesting. But I think what I found fascinating in watching this again was it's from 2006, so that's nearly 10 years ago, and yet we're still talking. You know, if you sat him down and he had that conversation or that talk, you'd say, oh, well, he just did it a few days ago. Right? Because he's still, same sort of comments about IPv4. Oh, well, we kind of ran out of addresses, or we know we're running out of addresses. Yeah, we're going to try to change to IPv6, but you know, it's hard and stuff like that. So we're kind of in the same state we were in 2015 as we were in 2006, at least in North America. Probably other places in the world have made more of a transition to IPv6 than we have. But for most of us, all of those comments that he made about IPv4 versus IPv6 are just as relevant today as they were 9 years ago. So I guess it sort of shows how slow progress is made sometimes and what everyone is up against. Okay. Okay. Oh, there's Bob's video. Let me get some lights back on. Okay, so last class, we were looking at routing. Well, we were looking at ARP, and we were talking about how does MAC addresses get used in routing and stuff like that. And so, I mean, the basic picture is something like this, where as far as routing is concerned, we only ever, of all of the protocol layers that get examined or used, we only use the first three, right, for routing purposes. So our packet comes along, it goes like that. Okay, so, and it's out again. It never goes up to the transport layer or to the application. It just goes to the network layer and then back out again. Okay. So just keep that in mind, just sort of a reminder. And what I want to switch to now is NATing, which is network address translation, or basically, how does your home router work? Because your home router works a little bit different, typically, than the big routers that you have in the internet or that have at UBC and stuff like that. So how do they work? Okay. So to understand this, we first have to understand the idea of connection multiplexing. Okay. And here's sort of the picture of connection multiplexing. Okay, so we have on the right-hand side a computer. Let's say on that computer is running a web server. And we have connected to it a wire, so that orangey thing there is the wire. And you're out there on your computer, and you're going to connect to that web server. Right? So if you do that, so there's the packet that you send out would have the address, say something like 123.212.67.56, and then 80 is the port number that you go to. So it would go to that. So go like that, end up at that machine. And if your friend was doing the same thing at the same time, they'd also have a packet that would go out with the exact same IP address and the same port number. And it would end up at that machine. So what's going on so that when the web server sends the answers back to those two different computers, it gets back to the right machine. That's one. But more importantly, how does it keep those two streams of data apart so it doesn't mix them up? How does it know that, if I back up a little bit, that this packet that I'm about to send isn't just a repeat of this other one? Because there's nothing that says that, if you have two different computers, that the contents of a packet are in fact exactly the same. They could be. Right? It could be that you both typed in the exact same URL, it goes to the same server, typed the exact same way, so everything looks exactly the same. So how do they straighten that out? Right? So how does the receiver keep these two streams of data separate?
Quick question.
Sure.
You mentioned before that the IP addresses are from both computers are the same, but in the diagram.
Oh. Okay, they are in fact supposed to be the same, so we will fix that. Maybe. As soon as I find my. Okay, I fixed it, now it's going to crash on me, right? Okay, see, now that's 56. Both 56 now. Okay, now we've got it right. Okay, thank you for pointing that out. Okay. So,
Shouldn't there be a router or computers?
there could be, but as far as, well, you would have seen the Socrative questions today. There were a bunch of questions about that. But the fact that there are routers in there doesn't affect what the destination address is, because every router, the routers just look at the destination address, they don't actually change it. Okay, so we can sort of get rid of the notion that, well, as far as this conversation is concerned, the routers are transparent to us.
So they could be on different networks, like the server and home, they could be on.
Yeah, they could be on different networks. They could be on the same network. They could be on different networks. In fact, what's to stop it from being on the same machine? Have you ever, I mean, I'm sure that you've done this where you have up one browser and you type a URL into it, type the same URL into a different browser, maybe even the same window of that browser. And it goes out there and connects. How does it actually, now the problem's even worse. In this case, it's coming from two different machines. Well, maybe it's not worse. But you can even make it so they're coming from the same machine. So, what information does the receiver need to be able to sort of figure this out? Or what information is it going to use to figure this out? Is it the port number? Okay, well, hold on, I have an idea. Why don't you guys talk amongst yourselves for a couple minutes, and then try and convince your neighbors or to come up with some ideas, and we'll write them on the board, and then we'll see where we're going with that. Okay? So spend a couple minutes, think about it, talk to your neighbors and say, okay, what do we need? Oh, what's the question? Okay, the question is, what information does the receiver need to be able to to keep those two things separate? Yeah. Stretch it. Okay. Try again. Okay, so any ideas? So we had one idea, right? Was, okay, so which port? You said port number.
Yeah.
Okay. So a little bit more.
I don't know.
Sorry? I'm sorry to put you on the spot. Okay. So, okay.
One thing the receiver doesn't need to know, like it will just respond to the IP address with the port number, and then
So hold it, the receiver doesn't need to know, what don't the,
If there are two different machines, the receiver doesn't know if it's coming from two different machines.
so you're saying that this guy doesn't need to know that it's coming from two different machines. Okay, why? I mean, it needs to get two different answers back.
It will get this two requests, and then it will just respond to both of them. And then on the way here, it will handle which computer will receive its data, like packet.
So how do we know to get the data to this guy as opposed to this guy?
Probably if the port numbers are the same, so we'll probably find it by process ID or something.
Okay, don't think you're quite on the right track there. Okay,
So the receiver needs to know the sender's MAC address, IP, whatever, and the sender's port number, so that it can send it to the right service. So we already have, or we probably have that from when the sender gives us a request. So then we just keep whatever service that we're running tied up with that sender's IP and port number. So then whenever we get to send a response, we send to that specific process.
okay, so let me try and, whoops. At least there's not a stage for me to back up off of, right? So that's, so let me try and capture what I believe you said. If I'm not capturing it, let me know, okay? So you're saying we have a destination IP address like that and a destination port, but the packet also has what is essentially a source port and destination, so let's call that X, Y, Z, and A. And it also has its own port number. Is that correct?
Yes. Well, you need to, otherwise you can have multiple services with the same computer.
Okay, 81, 81, let's say.
So the interesting question is, how do the senders, how do they actually use the same port in receiving end? That can't be the case. They can't both be using the same port. Maybe one is mapped to another port.
You mean talking about when it's both going to port 80?
Yeah.
Okay, so let me I'm going to just draw this out again here, okay? Okay, so I just want to put so the question that you raised was, okay, even though this part here is different, this part is the same, so what's happening on this guy to be able to look at this and figure out that these are different, right?
Yeah, because they can't, if they're one port, then you have one process that is executing differently.
Okay, so that's one, okay, so that's one problem,
Yeah.
okay? A problem is, I'm just going to put this as same port, okay? That's shorthand for what you said.
So, idea, back to the original question, is the sender sends something with it, some kind of identifying information that's put on the network or application layer, I think. It identifies them, like the MAC address or something.
So
The
you're,
receiver sends it back, but the router or something in between that's forking the two senders, it knows where to get to. So there's extra identifying information that the sender is sending.
so some other ID type information goes along with it, okay?
Even the receiver is sending it to the same IP, the router then gets it and knows where to give it to.
Okay. Okay, so there's a possible extension to that. Anyone want to comment or add anything to that?
Well, if a request consists of multiple packets, then those packets are going to all be numbered on the same machine. So, if we have that in combination with some kind of unique tag on in each of those packets, identifying which ones go together, then the sender would be able to take all the packets with the same tag and then stitch them together by the sequence number.
Okay, so,
And then it would know those are all
So-
requests.
well, I won't claim it's exactly what this your classmate was saying, but so some other ID tag, okay, plus a sequence number. We need that. Okay, that's sort of the extension.
Yeah.
Okay. Any other comments?
How does the sequence number give us any additional information? Because we already know we have a unique identifier for the sender. The receiver, if we rely on the sequence numbers, those could be the same for multiple processes.
Okay, so the points being raised here is that there is a potential that the sequence numbers are in fact the same. There's nothing to guarantee uniqueness as far as sequence numbers are concerned. And just to sort of highlight that, if every time you opened a connection, you started with sequence number 0, then there would be a really good chance that they're in fact the same. Ironically, they don't start with 0, though. They start with a random number for their sequence numbers, but for a different reason than what you might think. Okay, so it's got nothing to do with this particular problem. Okay.
If you keep adding extra information to the packet like this, wouldn't there be too much information just to hold along with the packet?
So your concern is that we're making our packets larger, and this probably isn't a good thing. That doesn't sit well with you. You don't have to be able to articulate it. I'm just sort of paraphrasing it, right? So you're uncomfortable with that idea that we're adding more information. It's not clear how much more information we need to add or what we really want to do with it, right? So that a little bit uncomfortable there with that, okay? Okay, so the answer is in fact on the board, okay? Ironically, we'll get rid of stuff to get the answer. Okay, so turns out we don't need any of that other stuff. Okay. However, let's go back and address the first, I think a more fundamental question was, what happens when they both go to the same port? Okay, how do we actually, I think the sort of the issue is, I'm at the program level, and if you look at your assignments, for example, you opened up a socket, you made a connection with that socket, and then you read from that socket, okay? And so you're the client side, you've made the connection, so you would be doing this. It actually turns out that on the, this is just a quick sort of overview, actually on the server side it's not quite so symmetric. In fact, on the server side it's a little bit different. What you actually do is you do something called accept. Okay. And what accept does is, okay, there's another command also called listen and bind, but we'll sort of ignore those for the moment. But accept is sort of a way that is the equivalent of answering the phone. So what happens is that the server sits there, and it will typically be in a loop. And it will go accept like that. Okay? Then it will do whatever it does and go back to the beginning. Okay? So you get so at any one point with this particular view, what happens is you do accept. And so let's just say we're doing that. Well, what would happen is if there were two connections, two requests coming in, it would pick one of those, and it would accept it. Okay? And now only the data from that one is going to go to the application. Okay? So don't worry about how we keep it straight yet. Okay? Just sort of say, okay, here's what's happening. You do the accept, and now when I do the accept, it's say this file descriptor is going to be hooked up with this stream of data here, and I'm only going to get this stream of data. We haven't addressed how we're keeping it separate, but from the application's perspective now, it has just a single stream of data coming in. Okay? Well, it turns out that if you did this in a thread, okay, so the typical one way of doing this is you do an accept, and then you start a thread to actually work with the data, and you go back and you do another accept. So now what you have is you have multiple threads, and each thread does an accept, which means that each thread could potentially get attached to its own sender, or own stream of data here. So, and that's actually what happens in, at least in some view of a web server, that's actually what happens, is the web server sits there and it goes, and it's doing nothing except accept. When it doesn't, when someone hits it with a connection request, so when you guys, for example, like in your assignments, when you do opens, right, you did an open against something, so that results in a connection request going out there. And the other side, if it answers, meant the other side had done an accept and had done this. And now, since it's in its own thread, everything is fine. So file descriptors are associated with a particular stream. Just like when you open a file descriptor in a program. Now I'm standing here and I'm trying to think about whether or not they tell you about file descriptors in 2.13. Do they tell you about file descriptors in 2.13? No. Okay. 3.13 they do. Well, let me put it another way. When you take 3.13 from me, you know what a file descriptor is. Okay? So a file descriptor is this, technically it's a small integer, and it's just a way of saying, okay, this is where I want to do my reads from. You do opens and closes and things like that on the file descriptor, you do reads and writes on them. So it's a sort of, instead of having a name for something, you essentially do open and associate a name with the file descriptor. Okay? And then you do reads and writes on it. Okay? And that's what's happening here. So you're doing your reads, you're doing your writes, and you could have multiple ones of those going on simultaneously. However, we haven't addressed the concern of, well, how do we know that this guy goes here to, let's say, file descriptor number 1, and this one is supposed to be going to file descriptor number 2. Okay? Is that right?
Yeah, so I was wondering, do we have some sort of table where we're binding between threads and...
Oh, okay, so how is it done? And you're exactly right. That is, in fact, what happens is within the operating system or the kernel, there is a table of file descriptors kept. And then they have a level of indirection or mapping that goes back to the incoming stuff. Okay? But so let's take a look at what we've got that's coming in. Okay, we've got, it's going to A, B, C, D, 80. And we've got A, B, C, D dot 80, or colon 80. Okay. So let's just look at that piece of information and say, okay, is that enough? So those are the two different streams. Okay. One of those is supposed to go to file descriptor number 1. One of those is supposed to go to file descriptor number 2. Okay. Is that enough information to figure that out? So if you just saw that information, could you tell which one it's going to? I'm seeing shaking heads. That's good. Right, we can't figure that out. Okay. But if I augment that with x dot y dot z dot a, and this one with c dot d dot e dot f, if I now treated all of this as one identifier, okay, as opposed to just looking at this part as the identifier. Okay. So if I did that, now I'm starting to be able to separate those two out. Because are those two identifiers equal? Well, I saw a nod. I think the answer should be no. Okay, they're not equal. Okay, so those aren't equal, which is exactly what we want. But what we have to be a little bit careful about is, could they be equal? Okay. Well, in this particular example, and in the first one that I had up there, they were coming from different machines. So the X, Y, Z, and A, and C, D, E, Fs are in fact different, so that's enough. But if they were coming from the same, yep.
Sorry, ABCD is the server's IP, XYZA is the sender's IP.
That's right, yeah, yeah. So this is the server, if I spell it out right, and the client here. Okay, server client part. Okay. Yep.
And we don't need the port number for the client.
Well, I'm going to get to the port number, okay? So the question was, and you don't need the port number for the client? Okay, the answer here is, well, actually we do. Okay, and I want to show you why we do. Okay, so if we have just this right at the moment, if they're on two separate machines, that's sufficient. But if it turned out that those requests were coming from the same machine, right, then the CDEF would in fact be X, Y, Z, and A. And now they would in fact be the same. And so now we would be back in our initial problem where we couldn't tell them apart. However, we do know that if they're coming from the same machine, okay, same computer here, right, that if this is client 1 and this is client 2, those are in fact two different programs. And so they will have two different ports. So if we augment that with the sender's port as well, or the client's port, so we'll put the port number on here, and now we have something that will be unique regardless of whether it's on different machines or the same machine. Okay? So and now we can use this as the thing that looks it up. So now what happens is the packet comes in. Oh, keep in mind that all of this information is in the packet already, right? I haven't added any information. Our packets always have source and destination IP addresses, and they have source and destination ports. But you'll notice now that the port part is actually in the transport layer. So when it gets to when we get to the destination machine, we're going to have to actually sort of start looking at some of this transport information to figure out which file descriptor we want it to go to. Right? So we'll take this and we'll say, okay, this one goes to this file descriptor, this one goes to this file descriptor here. And if we get another packet coming in, anything with that will be there as well. Now, just to go back to the notion of sequence numbers that was mentioned, okay, we won't address that right at the moment, but we will later. But if we look at a sequence number, what that would allow us to do is detect whether or not packets had been reordered while they were being sent and put them back into the right order if needed. You can also tell whether we lost something or not too, but that's another aspect of things. Okay? But for the moment, let's just assume that things are in order and we don't have to worry about the sequence numbers. So if we have that information, we can now get them to the different file descriptors.
Is it possible that a program on the client may send multiple separate requests from the same port?
Multiple separate requests. The answer to that is no. Because this has to do with how it's actually implemented. So a request is associated with a file descriptor. And so when you create the file descriptor through the open, you get exactly one request out of it. And so when you're done, you have to close it, and then you get a different port number. Okay. Unless you always love this part, right? You get a different port number, provided that you do it within a certain time window. If you do it longer than that time window, then you could get the same one over again. But that has to do with the notion that packets have lifetimes in the internet. And so you just have to wait longer than what that lifetime could be, and then you can reuse it. Okay. But that's getting really messy.
So
was this table thing with the file descriptors considered part, this operating system part considered to be part of the transport layer, or
Sorry, is it considered to be part of?
transport layer, or the net, application?
You mean, like, where is this done?
Yeah.
Well, it's done in the kernel. So it would be done, so it's one of those sort of interesting things where it has to kind of cross both the transport and the network layer to achieve it. So the kernel would be, the operating system, the kernel, would be looking at both transport layer and network layer information to do this multiplexing. Oh, okay. We started out with the term multiplexing. I guess I should define it now, right? Okay. So, but did that answer the question? Okay. So multiplexing is this idea that you have different things all going across a line taking turns in some fashion. Okay, so that means that in reality what's going on, although we have separate things like that, what really happens is they came over one wire, it goes along to one wire, gets to our machine, and then the machine in the kernel, so this is a boundary for the machine here. Whoops, that's not going to be very good. So what I'm trying to do with those lines is illustrate the fact that we had two different streams of data coming out, two different sets of packets coming out. At some point, they go across a common wire. Right? And so when they go across a common wire, that means that some of the packets, some packets from here, then here, and they go sort of back and forth. Just how many packets and stuff like that doesn't really matter. But the fact that if we look on this wire, that some of the packets are from this one and some are here, and they're alternating and things like that, that's the idea of multiplexing. Okay, so they're multiplexing across this. Then it comes into the machine. So they're coming into the machine multiplexed. And now what we have to do is we have to separate them out into their two different streams and head them towards the appropriate file descriptors. And the act of doing that is referred to as demultiplexing. Okay. So multiplexing is the act of taking separate streams, putting them onto one. Demultiplexing is the act of taking that single stream and breaking it apart into multiple streams. Questions? I'm seeing a few puzzled looks. Someone be brave.
Well, I just wanted to confirm, the two senders, they don't have the same IP address, right?
Sorry?
The two computers that are sending the packets, they don't have the same IP address?
That's correct. But they could.
So, but then wouldn't x.y.z.a be the same as c.d.e.f?
Sorry?
But if they have the same IP address, then wouldn't the two, then how would it?
Oh, if they have the same IP address? Okay, if they have the same IP address, so if they have both the same destination IP address and the same source IP address, then we have to look at that, then we have to look at the port number to separate them out. And we know that's going to be different because if we go to a single computer, which has one IP address, there will be conceptually multiple processes running, and there is a one-to-one mapping between port numbers and file descriptors. And file descriptors, there's another mapping between those and processes.
So different computers have to have two different IP addresses.
So,
If it,
no, they can have the same IP address. Oh, sorry. Sorry? Someone was going to clarify the...
If you can have two different computers that have the same IP, then they could both be using the same port number as well.
Oh, okay. Right. So it has to be the case for all of this stuff to work that no two computers have the same IP address. If two computers have the same IP address, it's not going to work. And then, okay, just to be clear, okay, and then I know there's my friend over here someplace or sat over there last class, but what's to stop them from having the same IP address, right? Well, there's nothing, okay, other than the goodwill of everybody wanting it to work, there's nothing to stop them from having the same IP address, okay.
So this isn't taking into account that, like, a machine being actually a router?
Sorry?
Like, if one of those senders was a router on a network, and there was multiple machines behind it, that were all like DHCP sending out, they'd all have the same IP address, right?
Okay, we're going to get to that. Okay, yeah.
So from the perspective of the receiver, the server, if the two senders are on the same network, the receiver will see it as one IP, even though it's two separate requests.
If not, no, the fact that they're on the same network doesn't mean that they don't have two different IP addresses.
Okay.
Right? So, yeah. Oh, here and then, yeah, okay.
I just want, I don't know if this is too specific, but going back to the question, when you have, when the packet's coming from the same IP, you would have two different ports. So like, I don't know if this is too specific, but if the browser sends like 2 pages, same server, it's guaranteed that it doesn't open 2 ports. So is the routing done by the browser?
Okay, so that's a different thing. Okay, when it sends 2 things like that, that actually is the application level that's making those separations. Okay, it's not being done at this level.
So as far as the server is concerned, it still will have.
It's still one. It's just as far as the servers. Sorry, as far as the networking aspect of things is concerned, it's just one big stream of data, right? And the fact that there are pages and stuff like that, that's imposed by the application layer. Yeah.
You mentioned web browsers. Does that mean that every tab on a browser uses a different port number?
Oh, that's pretty specific. I believe so you're talking about the source port number.
Yeah.
I believe the answer to that will be yes, right? So if you do okay, so if you want to test this out, okay, trouble is I don't really know the Windows commands for these, but the Unix command, okay, is netstat. So do netstat -a, okay? And this is where it gets, and if you want to sort of not have as much crap to look at, okay, do an fgrep -i TCP, okay? So we'll just look at the TCP stuff, okay? And what you should see, so what that will show you is all of the connections from your machine to another machine. Okay. And now that this is where the hard part comes in, you have to know, if you go and look at all of so you have to know the IP addresses of all of the machines that make up the URLs of your tabs. And if you look for those in this list, they will be there, and they will all have the same destination port. If they're on the same web browser, so they will have the same IP address, but they'll have different source ports. Okay? So if you want to try that out, go ahead. It's probably, you probably want to have your machine really quiet, so don't have a whole bunch of stuff going on at once, because there will be there are way more IP connections than you can imagine being set up for this stuff. And it can just get a little bit hairy following all of them. Okay, so any other questions? Okay, so what we'll do, now what we've got here is, this is connection multiplexing. And so what we're going to do is we're going to use some of the information or ideas from this to deal with the situation called natting routers, or how your home router works, where the machines that are on your home router aren't actually on the internet. And so they have a completely different IP address and stuff like that. So we'll look at that on Friday. Okay.
this guy didn't know.
No.
Oh, I see. No, it's only gonna get this lines up.
I think that's going to be
Trying to VPN force.
Unless we have reserved ports.
there are definitely ports, yes.
Try to power.
Yeah.
That says, you know, if it's port 80, it's
Felt bad.
20-something or other, it's this. So all ports can do
Does not send to power cycle server database.
Port has its own single threads, or do they all just go to the same?
Oh, okay.
Actuating. No. It's just that was so hot that thing was so fast.
If it did, then we'd all be dead.
It is. I went to the hipster fair.
Seriously? They gave you a free jacket?
No, I bought it.
Oh, okay. I was like, man, you must have been pulling serious hipster stuff.
I wish I could just like go like this. I'm assuming with the network.
We'll be able to know the
It's just that because it's having port numbers only.
My parents are not.
But then when you're doing it for the same computer, why is it sending it to different points when you actually have the same information on the
Part of the package that's used by the network layer is the just have one.